Hey Cap 3 class, we are going to start into the last chapter and we are dealing with a concept called vector fields. So what is a vector field? It's defined to be a function that takes in elements of the domain and spits out a vector. So what do we mean by that? So if you give me a point in the plane, alright, so R2 or R3, we'll start with R2. If you give me a point in the plane, what's going to happen is at that point we're going to begin a vector, and that vector is going to be defined by the x and y coordinates of the point where it's supposed to start. And we make the vector begin at that point and it goes away from that point depending upon what the definition of the field is. So let me give you an example. So here is an xy plane. So let's say that we have a vector field, a very basic one, f of xy equals xy. Okay, so the point that we plug in into the function, remember this in parentheses is the input, and our input is a point. What do we do to that point? We begin a vector whose components are the point. So what does that mean? Well, let's think about if I were on the x-axis at the point 1, 0. Alright, what am I going to do? Well, if I plug in 1, 0, that means I have the 1, 0 vector. The 1, 0 vector moves to the right 1 unit, and there's its head. Alright, the 0, 1 vector, if I plug in that point into the function, what's it going to do? It's going to make the vector 0, 1. Alright, if I plug in the point 1, 1, alright, what am I going to get? I'm going to get the vector 1, 1, which would point up into the right like that. That's the point 1, 1, and that's the vector 1, 1. So basically, how far I've moved from the origin to get to the point is also how I'm going to move away from that point. Alright, the vector -2, +1. Alright, I moved over to the left 2 and up 1. I'm going to go over 2 and up 1. And that will be where my arrow ends. Let's pretend that's a straight arrow. So at every point we're getting a vector coming off of that point. And I've got a website up here and I've got linked on Moodle where you can input the vector in the IJ notation. So this was 1xi plus 1yj. And as you can see, what's happening is, whenever I go to the point, I get a vector that points in that direction that I've traveled to get to that point. Okay, so we're going out from the inside. Now these have been scaled down, obviously. So this is the point -1, 2, 3, 4, 5, -1, 2, 3. That's obviously not going to left 5 and down 3. It's been scaled, and we do that often because if we don't, we have vectors that run into one another. So this is scaled down by 1/10. If I don't scale it down, it gets chaotic, and you can't plot everything, and that doesn't give us any useful information. So oftentimes, vector fields are scaled to give the idea of what's happening. We're moving away from the origin in this vector field, and the magnitude of the vectors that we're getting is growing. We get that information from this nice, pleasant-looking version of it, just as well as we do from this one. And this one's just chaotic and immediately it's hard on the eyes, even for numbers really close to the origin. So it's a very common thing to scale your vector fields to be able to see the vectors even in the most extreme points of your graph, to be able to see them be contained within a single cell of your grid. Alright, let's look at the field yx. So all we do is a switch. So what happens at the point I make a vector, and now the vector is the horizontal motion is given by the y coordinate, and the vertical motion is given by the x coordinate of the original point. So I'm going to plot a few points on here where we're going to do this, and then we'll come up with what would the vectors look like there. Alright, so let's start here at the 2, 0 point, and what are we going to do? We are going to make a vector. This is 2, 0. The components of the vector are going to be 0, 2. Alright, and then I'm going to do the same thing for all these points, and then we'll talk about what happens. We're just switching the x and y coordinates. So whatever the x coordinate is, it becomes the y component of the vector. Whatever the y coordinate is, becomes the x component of the vector. Alright, now let's scale these down. Obviously, this is starting to get a little chaotic, but let's scale these down a bit, and we get something that looks a little like this. Now, this doesn't, we have arrows that are seemingly going in all these different directions, and it doesn't seem like there's any rhyme or reason to it. But let's think about what's happening in each quadrant. So in this quadrant, x is positive, y is negative. So what's going to happen when we're in this quadrant? Well, if we flip it, we're still going to get right and up motion because everything's positive. So no matter where we are here, we're going to be moving to the right and up. Along the x-axis, x's are positive, y is 0. If we switch it, we're going to get upward movement, and it's going to get higher the further we go out. Along this axis, we're going to get movement to the right. So we're going to the right, we're going up, and we're going out. So this one has this motion of up and to the right and then up in this quadrant. And this one, x is positive, y is negative. So when we flip it, we'll be moving to the left and up. So left and up in this direction. All right. On the negative y-axis, we're going to be moving to the left because x is 0, y is negative. And then the same thing in these quadrants. In this one, x is negative, y is positive. So when we flip it, we're going to be moving right and down. Here we're going to be moving left and down. So in all these quadrants, we have we know what the motion is going to be like. But here's the thing, these lines that go through the origin, where the x and y coordinates are equal, they're going to be moving perfectly diagonal, like 45-degree angles through these quadrants. And they're going to be the ones that decide which way our motion goes. All right, let me pull this up in that vector field plotter so we can see a lot of arrows, and they're not nice and scaled down. So what's happening here is there are these lines like y equals x and y equals negative x that are giving us a kind of a place where these fields split. And what I mean by that is if you're above the y equals x line, up here, your motion initially in this quadrant is going to start down. You're going to cross the axis, and then you're going to go up. And in these y equals x, y equals negative x lines are like asymptotes, that the behavior of the field is either moving away from or moving towards, or both, depending on where we start. And then the same thing down here. If I'm down here and I pick a point, it's saying move towards that y equals x line. If I'm down here near that y equals x line, I'm going to start up, and then I'm going to move to the right and then come back down. If you give me a point that is known to be in this field, let's say my point is, let's say it's right here. What I get to do is these arrows guide me into the path that I would take. So this arrow right now is saying, all right, go in this direction. And then when you get here, turn and maybe go in this direction. And then you got to understand, I'm plotting a finite amount of it, but there's an infinite number of these. So no matter where I go to, I'm being guided into a new direction of how to proceed through the field. and they are sending me ultimately down in this direction. So if you give me an initial point to go along with the field, then I get a path that I would take through the field. And the step size I would take could be determined by a preset definition that for every point I'm going to move in the direction the field tells me to, a half a unit. And then I'm going to turn and update which way I need to go and turn it up. So if that sounds familiar to you, it is. It's Euler's formula. It's exactly the same thing as numerically solving a differential equation. And also in the single variable version of this, so if you give me an x instead of an x and y, if you just give me an x for any point that has that x coordinate, let's say that the slope at that point would be 2x. So y is not making any difference here. Y is not playing any role into it. So, at this point, -2, +2, the slope is -4x. All right. And at -2, +4, the slope is also -4x. At -2, -1, the slope is -4. Okay. So the y coordinate doesn't matter because this is the single variable version of this. And as I move, all I'm doing is doubling the x coordinate, and that's giving me the y coordinate. I'm sorry, that's giving me the slope at that point. All right, so that would look something like that. Well, if you kind of look at that pattern that we're seeing there, if I collect all of those values, I would get something that looks like this in the single variable version. And then if I just add a point to it, there's a point 2, 1, I would get this. All right, well, maybe my point, instead of it being that, is that point, or maybe that point, or that point. The idea is, if you give me a single point in here, and let's see if I can move that, go to that point, that's a known point and a slope field, so that's where we would move down. If I move that point, if I move that known point, what is it doing? It's just shifting the graph vertically, right? It's just shifting the graph vertically. It's still got that same shape no matter what. Well, this is the idea of the plus c when you're doing an antiderivative. So this is just dy dx in the single variable version. Dy dx, the slope at any point in the plane, is 2 times the x coordinate. That would look like this slope field. And if I add a known point to that and move that point to anywhere I want to, what do I get? I get a unique solution. So there's all these possibilities that I could get for a solution, but if I have a known point, I get a unique solution that it goes through there. So that's exactly what we're doing with this. It's just now we have the capability of the derivative having multiple variables. It's got x's and y's. So the slope, if you will, it's a vector. How we're changing at a point is given by 2 variables now instead of just a single variable. But the concept is still the same. If we think of this as a bunch of slopes at a point, derivatives at a point, now we can get motion in the x and y direction, how we're changing in both directions. And it's not just determined by the x coordinate. If it was, then all these arrows would be pointing in the same direction. Now we are able to change as we move up and down instead of just left and right like it was in single variable calculus. All right, so we see vector fields used a lot. So weather maps, if you see wind layered on top of a weather map, that's depicted by a vector field. And those of you who have ever seen in physics and engineering, Bernoulli's principle, where we're talking about wind velocity, and we have this airfoil and it's bending up and around, and this is very common when we see these things, and a lot of the time these arrows meant velocities, like it did here, like it does here. And we use that a lot of times. We actually call vector fields velocity fields because that's what they're used to represent, is how something is changing in an image or in some type of a model. All right, and the other thing that we use vector fields for in modeling, especially in physics and engineering, is force fields. So the vectors themselves, instead of representing velocity, they could represent forces acting on some type of phenomenon. So some of the applications there is Newton's law of gravitation can be modeled via a force field. Coulomb's law is as well. Similarly, with the attraction of objects, it also deals with repulsion if they have the same charge. Anyway, that's another phenomenon that can be modeled with force fields. And in both of those cases, we see that the origin, or it doesn't have to be a single point, it can be like a line in space. But in this case, in both of these pictures, it's a single point. And in a repulsive force field, everything is moving out away from that. And in an attractive force field, everything's being pulled in. Sometimes we call these sinks. Everything's coming into it, and sources of things are going out from it. Now, you guys have already seen a vector field this semester, and that's the gradient. Because think about it, what did the gradient do? It took in a point and it spit out a vector. That's exactly what a vector field is defined to be. If we take in a point and we spit out a vector, we're a vector field. That's what the gradient did. So the gradient was the first example of the vector field that we saw this semester. And we even call these fields the gradient. We call them the gradient fields sometimes. All right, so determine the gradient field of this scalar field. So what does it mean by that? The scalar field, this function takes in a point and it spits out this for the height. All right, that's the scalar field. It gives a number. So the scalar being what we're used to. You give me a point and I go up or down based on the number that I get. I go up that many units or down that many units. But if we take that and come up with the gradient of that field, then we get the function y squared. Okay, we get again the derivative with respect to x would be y squared minus 2x, and then the derivative with respect to y would be 2xy, and then the minus x squared would be 0 because there's no y's in that. So there's our gradient field, and we could plot several of those. We could do the same thing that we've been doing. All right, and we get something that looks like this. This is how I'm getting the I components. This is how I'm getting the j components. And I've got this field. I've scaled this way, way, way down. All right, because these things are huge vectors if I don't scale them down as we move away from the origin. But anyway, we see that motion. We see that it goes down, it turns, it goes back up. This goes up, it turns, it goes back down. So we see these along this axis. We're pulling into the origin. But if we're not exactly on it, we get pulled in and then we get repelled as we make our way past the y-axis. And the same thing here, we're getting pulled in, but then we get repelled. All right, we've got a very, very, very important definition here. If the vector field that we're dealing with, if it can be written as the gradient of some function f, so that the vector field that we're working in is some other function's gradient, then that is called a conservative vector field. And f, whose gradient our field it can be defined as, is called the potential function for f. And if our vector field is some function's gradient, being a conservative field has very important ramifications to stuff we're going to do later. So if we can have this, it's going to give us properties that make some of the math that we do much easier. In some cases, from very difficult to nothing at all, very easy.